Close your eyes and imagine standing on the factory floor of 1890. The air is thick with the acrid smell of molten metal and machine oil. The ground trembles beneath your feet as massive steel hammers pound in a deafening rhythm. Above you, a web of electrical wires crackles with invisible power. And for the first time in human history, the darkness of night has been banished by the glow of incandescent light. Using advanced AI technology, we have transformed century-old photographs, engineering blueprints, and faded illustrations into photorealistic scenes of this vanished world. Today, you will not just learn about the second industrial revolution. You will walk through the smoke-filled steel mills of Pittsburgh. You will stand beside Thomas Edison as he illuminates the streets of New York. You will witness the moment humanity seized control of forces that would have seemed like magic to every generation that came before. The first industrial revolution gave us steam and iron, but what happened next would dwarf it entirely. Between 1870 and 1914, two forces emerged that would build the skyscrapers, power the assembly lines, and wire the world into a single nervous system. Steel and electricity did not just improve our civilization. They created the modern world we still inhabit today. But here is the question that echoes through this era. When humanity gains the power to reshape the earth itself, who decides whether that power builds or destroys? The first industrial revolution had been powered by coal and steam. It had transformed Britain from a nation of farmers into a nation of factories. But by the middle of the 19th century, that revolution was maturing. The great textile mills were humming along predictably. The railways had connected the major cities. The steam engine, once a marvel, had become ordinary. The world had grown accustomed to the rhythm of the machine age. But in the laboratories of inventors and the boardrooms of a new breed of industrialists, a second revolution was already stirring. This one would not merely improve upon the first, it would dwarf it. Between 1870 and 1914, humanity would harness two forces that would reshape civilization more profoundly than anything since the discovery of fire. Steel would give us the skeleton of the modern world. Electricity would give it a nervous system. Together, they would create the 20th century. To understand the magnitude of this transformation, we must first recognize the limitations of the world that came before. The first industrial revolution had been built on iron. Iron was strong, but it was also brittle. It cracked under stress. It rusted quickly, and producing it in large quantities required enormous amounts of fuel and labor. A bridge made of iron was an engineering triumph, but it was also a constant maintenance nightmare. The rails that carried the locomotives wore out quickly and had to be replaced. The machines in the factories broke down with frustrating regularity. Iron was the best material humanity had, but everyone knew it was not good enough. The problem was not a lack of knowledge. Scientists had understood for centuries that steel, an alloy of iron with a small amount of carbon, was far superior. Steel was stronger, more flexible, and more resistant to corrosion. But producing steel was extraordinarily expensive. It required heating iron to extreme temperatures and carefully controlling the carbon content. A single pound of steel cost 10 times as much as a pound of iron. It was used for swords and surgical instruments, not for bridges and buildings. Steel was a luxury. And then, in 1856, a British inventor named Henry Bessemer changed everything. Bessemer was not a trained metallurgist. He was a professional inventor, a man who made his living by solving practical problems. During the Crimean War, he had been working on a new type of artillery shell, and he realized that the iron cannons of the era were too weak to handle the pressures involved. He needed steel, so he set out to find a cheaper way to make it. His solution was elegant in its simplicity. He discovered that if you blew cold air through molten iron, the oxygen would combine with the carbon and burn it away. The process generated so much heat that it kept the metal molten without any additional fuel. In just 20 minutes, A Bessemer converter could transform tons of pig iron into high-quality steel. The impact was immediate and staggering. The price of steel collapsed. Within a decade, it had fallen by more than 80%. Suddenly, steel was not a luxury. It was a commodity, and the world rushed to use it. The railways were the first to benefit. Steel rails lasted 10 times longer than iron rails. They could carry heavier loads at higher speeds. The great transcontinental railroads of America, the Trans-Siberian Railway in Russia, and the expanding networks of Europe were all built on Bessemer steel. But the real transformation came when engineers realized that steel could do things iron never could. In 1885, a young architect named William LeBaron Jenney was designing a building in Chicago. The city was booming, land was expensive, and his clients wanted to build upward. But traditional construction methods limited buildings to about 10 stories. The walls at the bottom had to be thick enough to support the weight of everything above, which meant that the higher you went, the less usable space you had on the ground floor. Jenney had a radical idea. Instead of making the walls bear the weight, he would build an internal skeleton of steel beams. The walls would simply hang on this frame like curtains. The home insurance building, completed in 1885, was only 10 stories tall, but it was the first true skyscraper. It proved that buildings could go as high as the steel could reach. Within a generation, the skylines of American cities were transformed. New York, Chicago, and Pittsburgh sprouted forests of steel towers. The Flatiron Building, the Woolworth Building, and eventually the Empire State Building were all made possible by cheap steel. But the skyscraper was more than an architectural novelty. It was an economic revolution. By allowing businesses to concentrate thousands of workers on a single city block, the skyscraper created the modern corporate headquarters. It made possible the giant bureaucracies that would come to define 20th century capitalism. Across the Atlantic, one man came to embody the steel revolution more than any other. Andrew Carnegie was a Scottish immigrant who had arrived in America as a penniless child. He worked his way up from a telegraph operator to a railroad executive, and he understood better than anyone the potential of steel. In the 1870s, he began buying up steel mills, coal mines, and iron ore deposits. He integrated them all into a single, ruthlessly efficient operation. His philosophy was simple: cut costs relentlessly, undersell your competitors, reinvest every profit into more capacity. By the 1890s, Carnegie Steel was producing more steel than the entire nation of Great Britain. Carnegie was not a gentle employer. His mills ran around the clock, 7 days a week. Workers endured 12-hour shifts in conditions of extreme heat and danger. The Homestead Strike of 1892, when workers at his Pennsylvania mill fought a pitched battle against private security forces, became one of the bloodiest labor conflicts in American history. But Carnegie also became one of the greatest philanthropists the world had ever seen. He believed that the wealthy had a moral obligation to give away their fortunes. He built libraries, universities, and concert halls across America and Britain. The contradiction of the man mirrored the contradiction of the age. The Second Industrial Revolution created wealth on an unprecedented scale, but it also created misery on an unprecedented scale. While steel was giving the world a new skeleton, electricity was giving it a new nervous system. For most of human history, the night had been dark. The only sources of artificial light were fire and candles, which were dim, dangerous, and expensive. The wealthy could afford oil lamps and later gas lighting, but even these were feeble compared to daylight. The rhythm of human life was still dictated by the sun. When darkness fell, most activity ceased. And then, in the span of a single generation, the night was conquered. The story of electrical power begins with a fundamental scientific insight. In the early 19th century, scientists like Michael Faraday discovered that electricity and magnetism were intimately connected. A moving magnet could induce an electric current in a wire. This principle made it possible to build generators that could convert mechanical motion into electrical power. But for decades, electricity remained a scientific curiosity. It was used for telegraphy and for novelty demonstrations, but it had no practical application in everyday life. There was no way to store it, no way to transmit it over long distances, and no devices that could use it. The man who changed this was Thomas Alva Edison. Edison was not the greatest scientist of his era, but he was perhaps the greatest inventor. He understood that invention was not about isolated flashes of genius. It was about systematic experimentation. He built the world's first industrial research laboratory in Menlo Park, New Jersey, a facility dedicated to producing inventions on demand. He called it an invention factory. In 1879, after thousands of experiments, Edison and his team produced a practical incandescent light bulb. It was not the first electric light. Others had demonstrated the principle before, but Edison's bulb was the first that could burn for hundreds of hours without failing. More importantly, Edison understood that a light bulb was useless without a system to power it. Edison did not just invent the light bulb. He invented the entire electrical infrastructure that made lighting possible. He designed generators, switches, fuses, and meters. He laid the first underground electrical cables. In 1882, he opened the Pearl Street Station in Lower Manhattan, the world's first commercial electrical power plant. It was a modest beginning, supplying power to just 85 customers. But within a few years, electrical power stations were spreading across the industrialized world. The night was no longer dark. Factories could run around the clock. Streets were illuminated. The pace of urban life accelerated. But Edison's system had a fundamental limitation. He used direct current, which could only be transmitted short distances before losing too much power. This meant that power stations had to be located close to their customers, which made electricity expensive and limited its reach. The solution came from an unlikely source. Nikola Tesla was a Serbian immigrant, a brilliant and eccentric engineer who had worked briefly for Edison before the two men had a bitter falling out. Tesla was obsessed with alternating current, a form of electricity that reversed direction many times per second. Alternating current could be easily transformed to higher voltages, which allowed it to be transmitted over long distances with minimal loss. Tesla found a champion in George Westinghouse, an industrialist who saw the commercial potential of AC power. The battle between Edison's direct current and Tesla's alternating current became known as the War of Currents. It was a vicious public relations fight. Edison, desperate to protect his investments, staged public demonstrations where he electrocuted animals with alternating current to prove it was dangerous. He even secretly supported the development of the electric chair, hoping that its association with AC would frighten the public. But the technical superiority of alternating current was too great. It could power factories miles away from the generating station. It could light entire cities from a single plant. By the mid-1890s, the war was over. Alternating current had won, and the modern electrical grid was born. The implications went far beyond lighting. Electricity could power motors, and electric motors transformed manufacturing. In the old steam-powered factory, all the machines were connected to a single central engine by a complex system of belts and shafts. The factory had to be designed around the power source. The machines could not be rearranged without enormous effort, but an electric motor could be attached to any individual machine. Each piece of equipment could be placed wherever it was most efficient. This freed factory designers to optimize the flow of production in ways that had been impossible before. The electrification of industry made possible a revolution in manufacturing methods. The assembly line, though it drew on earlier ideas, reached its full potential only with electric power. Henry Ford did not invent the automobile. That honor belongs to European engineers like Karl Benz and Gottlieb Daimler. But Ford transformed the automobile from a toy for the wealthy into a necessity for the masses. His innovation was not technological but organizational. At his Highland Park plant in Michigan, Ford arranged the production of his Model T as a continuous flow. The car moved along a conveyor belt, and each worker performed a single specialized task as it passed. What had once taken 12 hours now took just 90 minutes. The price of a Model T fell from $850 in 1908 to just $260 by 1925. The automobile, once a plaything of the rich, became the defining technology of 20th century life. The Second Industrial Revolution was not confined to America and Britain. Germany emerged as a formidable industrial power, in some ways surpassing the nations that had led the First Revolution. The Germans were particularly dominant in two new industries that electricity and chemistry made possible. The chemical industry transformed agriculture and warfare. German scientists discovered how to synthesize dyes, drugs, and fertilizers from coal tar. The Haber-Bosch process, developed in the early 20th century, made it possible to extract nitrogen from the air and convert it into ammonia. This single innovation allowed for the mass production of synthetic fertilizers, which would eventually feed billions of people. But it also made possible the mass production of explosives. The same factories that fed the world could arm it for destruction. The electrical industry was equally revolutionary. German companies like Siemens and AEG became global leaders in electrical equipment. The Germans pioneered the research university, institutions that combined teaching with systematic scientific investigation. They produced a stream of discoveries in physics and chemistry that fed directly into industrial applications. By 1914, Germany had become the world's second largest industrial economy, trailing only the United States. But the social consequences of this rapid industrialization were profound and often painful. The new factories demanded a new kind of worker. The craftsman who had mastered a complete trade was replaced by the operative who performed a single repetitive task. Frederick Winslow Taylor, an American engineer, developed what he called scientific management. He studied workers with a stopwatch, breaking down every job into its smallest components, and then redesigned the work to eliminate all unnecessary motion. Resistance to his innovations earned his followers the name efficiency experts, a term that was not always meant as a compliment. Workers found themselves reduced to extensions of the machines they operated. The pace of work was set by the conveyor belt, not by human judgment. The response was a wave of labor organization and unrest. The late 19th and early 20th centuries saw the rise of powerful labor unions and socialist political parties. In America, the Knights of Labor and later the American Federation of Labor fought for better wages and shorter hours. In Europe, socialist parties became major political forces. The German Social Democrats, despite being suppressed by Bismarck, grew into the largest party in the Reichstag. The conflict between capital and labor became the defining political struggle of the industrial age. The Second Industrial Revolution also transformed communications in ways that shrunk the world. The telegraph had already connected continents by the middle of the 19th century, but it was limited to trained operators who could read Morse code. In 1876, Alexander Graham Bell patented the telephone, a device that allowed ordinary people to speak directly to each other across vast distances. The implications were revolutionary. Business could be conducted in real time. Families separated by migration could hear each other's voices. The telephone network grew with astonishing speed. By 1900, there were nearly 2 million telephones in the United States alone. Guglielmo Marconi went even further. In 1901, he transmitted the first wireless signal across the Atlantic Ocean, proving that radio waves could carry messages without any physical connection. The age of wireless communication had begun. Within a few years, ships at sea could call for help in emergencies. The sinking of the Titanic in 1912 demonstrated both the power and the limitations of the new technology. The ship's distress calls brought rescue vessels, saving over 700 lives. But the lack of a 24-hour radio watch on nearby ships meant that help arrived too late for more than 1,500 others. The Second Industrial Revolution reached its crescendo in the years before the First World War. The great powers of Europe and America had been transformed by steel and electricity. Their cities blazed with light. Their factories poured out goods in quantities that would have seemed miraculous a generation before. Their armies were equipped with weapons of unprecedented destructive power. Machine guns, artillery, and battleships were all products of the new industrial age. The same forces that had built the skyscrapers and the assembly lines would soon be turned to the work of destruction. When war came in 1914, it was an industrial war. The combatants mobilized their entire economies for the struggle. Factories that had made automobiles now made tanks and artillery shells. The chemical industry produced poison gas. The electrical industry produced communications equipment. The war consumed men and materials on a scale that no previous conflict had approached. The Battle of the Somme, fought over 5 months in 1916, resulted in more than 1 million casualties. The industrialization of death had arrived. But the war also accelerated technological change. Necessity drove innovation. The airplane, barely a decade old when the war began, was transformed from a fragile novelty into a serious weapon. Radio communication became essential for coordinating armies spread across hundreds of miles of front. The internal combustion engine powered not just automobiles, but tanks and trucks that would eventually break the stalemate of trench warfare. The Second Industrial Revolution had created the modern world. The war would determine who would inherit it. Looking back from our present vantage point, the Second Industrial Revolution appears as the true birth of modern life. The first revolution had created the factory and the railway. The second created the electrical grid, the telephone network, the automobile, and the skyscraper. It created the giant corporation and the assembly line. It created the research laboratory and the consumer economy. The world of 1914 would have been recognizable to a time traveler from our era in ways that the world of 1800 would not. The bones of our civilization were cast in steel during those decades. The nerves were wired with copper. We are still living in the world that the Second Industrial Revolution created. Our cities are still built on steel frames. Our lives are still powered by electricity. The struggles between workers and employers, between efficiency and humanity, between progress and its costs, are still with us. The inventors and industrialists of that era did not know what world they were building. They were solving immediate problems, chasing profits, and pursuing their own visions. But their choices shaped the century that followed and continue to shape our own. The Second Industrial Revolution was not just a transformation of technology. It was a transformation of what it meant to be human in an industrial society. It demanded new forms of organization, new ways of working, and new ways of thinking. It created wealth beyond the dreams of earlier ages and poverty that seemed all the more cruel by contrast. It connected the world and armed it for conflict. The steel and electricity that built our modern life also cast long shadows that we are still learning to navigate. I'm Michael, watching the past so we can understand the present, and together we keep history reborn. I'll see you in the next era.